world now. And this profile can also be seen in cross-sectional profile. Where the cross-section was expected, like in a downstream of water and downstream of water. In both of the cases, we found very stored document. That means it carries less element compared to its carrying capacity. That when it started storing the carry. Though the store is not too much or is not significant, but the idea was to initiate the process and we can follow. So finally we can conclude. Segment generated with time duration and tragedy buzzer. It is a simple condition. And a proposal model has been deployed, as I mentioned earlier, for simulate the river behavior and to investigate the contribution of bank theory segment. Model derivation were found in the next 2 minutes. And I don't recommend bank quotation works at upstream of work. And adopting the recommendation, both base model and model with bank quotation was simulated. And for the with the model with bank works generated gas amount selection and with the base solutions. So finally, it can be concluded that the date of mathematical modeling, the morphological modeling is possible to assess the impact of human morphology for any human intervention and thereby guide the planners and policy makers. Thank you for your attention.
I'd like to thank Massimo Raffon for a clear presentation and staying right on time. Any questions from the audience? One.
In 1 year or 2 years,
it's about 1 month soon, 1 year.
And then I saw, this my interpretation in my bed. This is hydrophobic. Thank you.
Question actually. In the model, you studied sedimentation, so definitely it should be affected by the local vortex dynamics and the calculus. Do you think that your resolution was fine enough to capture the full physics? Because so far as I understand, you have calibrated your data with one experimental data, they should match. Because you didn't validate with other data, because so do you think that your grid size is
fine enough? You're right, it's not that much fine, but it's not possible also to work like into finite grid. And also when we have the very fine model, it doesn't work. So sometimes we need to make some custom model.
Thank you. And the last paper is by Mai Rahanan and Anir Starman. It all is static and dynamic analysis of semi-submersible black floaters for offshore wind turbine. We have to get out of here before the dinner is served at 7. So.
My name is Panis Silva. I'm from my interest. I'm going to present some results on semi-submersible pipe floaters. It's meant for supporting an output in Tata. So my daughter is a student and completed this work and has gone into a PhD student and knowledge. So I'm going to present a it has less turbulence intensity, smaller shear and shear than on land, no limitations for wind turbine, no visual noise effect. So when people installed this offshore wind turbine near the coastal community started complaining about good noise it's producing. So people started moving the wind turbines far off the coast. No space constraints. So we need to design suitable floaters for supporting this offshore wind turbine. When we think of floaters, how it is going to give stability such a massive structure. And one, you can think of water plane area. The moment that the structure, the water plane area makes about the structure center of rotation. For example, is a barge. And they have a ballast stabilized floater. And the lower the center of gravity, below the center of buoyancy. That's the spark platform concepts. And actually, there is a floating offshore wind turbine spark which is existing. I think, if I'm not mistaken, in Denmark or Norway. And there is some concept based on TLP, restore moment at the mooring line fixed on the structure. So we can achieve floaters stability with all these concepts. What we took is we had three different types of floaters: a barge-type floater, a semi-submersible floater, a deep-drafted column structured floater. And this is a part of the results of a semi-submersible type floaters. And it's different because we have four pontoons, and we had a parametric study of varying the height of the column, the height of the pontoon, the diameter of the pontoon, the diameter of the column. So that was the structure we had in mind for supporting the offshore wind turbine. Now the wind turbine we have considered as NREL 5 megawatt wind turbine. And it is not a real wind turbine, but it's a concept. Its rotor orientation is upwind, variable speed, diameter is about 126 meters, the hub height is 92 meters, and the total mass we are talking is about 730 metric tons. So that is the NRL wind turbine they have taken for designing the floater. Now we designed the semi-submersible for the supporting the 5 megawatt wind turbine, and did hydrostability analysis for the floaters. We did hydrodynamic analysis of floaters using WOMIC. And once we did these two cases for the different types of semi-submersibles, and based on the ROs, we chose which is the best type of floater, what we think based on the ROs, and then we did the response analysis for different sea states. So this is the driving parameters in water plane area of semi-submersibles at the water plane, and then how much pitch motion to be allowed to limit 10 degrees beyond which the wind turbine loses substantial efficiency. And when we design semi-submersibles and compare, we have to compare on one platform. So the platform we took this fixed metacentric height of 1 meter. So we designed all the semi-submersibles the fixed metacentric height of 1 meter. These are the load calculations on the rotor, the thrust motions, and what is the steady state field angle, and then what is the design restoring moment from the structures. So we analyzed 6 different semi-submersibles varying from square deck and a fixed GM of 1 meter, varying the diameter of the column to the diameter of the pontoon. And the floater mass has been varied from 2,280 tons to 2,400 tons, and the ballast was varied from 3,360 tons to 4,080 tons for the 6 different models, so that we have achieved the fixed GM of 1 meter. These are the different hydrostatic and mass for the case of the 6 different models. The protein diameters vary from 9.8 meters to 14.6. The pontoon heights, the column diameters to the column heights. Let me skip all this data. It's important to know that all these semi-submersibles are having a fixed metacentric height of 1 meter. And we did the student did the modeling using multi-sub for semi-submersibles, and hydrodynamic analysis was carried out in WOMIC. And one important thing to note is that while carrying vomit, which is a potential flow analysis, this diameter of the columns somehow some in a positive horizontal track. So we have to introduce artificial damping to bring down the RAOs. So that was based on some of the experiments which was conducted previously, and where people use vomit analysis for semi-submersibles, and then did experiments in the wave tank, and then they found what amount of damping we can introduce in the vomit to bring down the responses. So the same concept was utilized here, and 4% of damping was reasonable to bring down the responses, huge responses produced by vomit. So these are the results pertaining to the surge RAO for the different types of semi-submersibles of different diameters and column heights, the heave RAOs and the pitch RAOs. And from this, the flows of say V by D of 1.5 and H of 1 produce the least heave responses. And if you compare the pitch RAOs, all are relatively small. This is for wave heading of 0 degrees. Then the same analysis was carried out for wave heading of 45 degrees. And we did again the response analysis using the wave data for the best semi-submersible program. And the environmental data for sea states